I'm really sorry about the quality of the projector. I hope that it is visible to those who are at home watching this, or it's Grace watching it on the bus back from Birmingham. We are at the final part of differentiation, so we're basically through all the different things that we could differentiate, and what we're doing today is an application of differentiation, which I'm calling related rates of change. If you look at the Physics and Maths Tutor revision page that I pointed you to in OneNote, it's referred to as connected rates of change. There we go. This is a little bit weird, I have to say, all right? It's not sort of super straightforward in terms of, like, when we differentiate a bracket, we say, right, you multiply the power, reduce the power by 1, and then multiply the what you get when you differentiate the bracket. It requires you to be a little bit light on your feet. And by that I mean, I can't really say that there's this sort of problem, this sort of problem, this sort of problem, and to do that when you do this, and to do that when you do this, and to do that when you do this. You've just got to sort of use your nous sometimes and work through things. But anyway, we'll get through as many examples as we can today and give you a chance to do some independent practice as well, hopefully. These questions are all about rates of change. So when we talk about the rate at which something is changing, we can describe that as a d something by dt expression. Now we're used to seeing dy by dx, aren't we, when we differentiate a y is equal to something to do with x expression, and we know that this gives us a formula for the gradient. If something talks about the rate at which something's changing, it's d whatever that thing is by dt. T is the variable when we're talking about the rate at which something is changing. So we're not talking about y and x, we're talking about time. Where did I put them? Over there, we might. And so my esteemed and outstanding retired colleague, Mrs. Humphrey, would always say, when you're asked for a rate, you differentiate. So that's something to remember. These questions tend to start with some sort of geometry fact, normally an area or a volume, that can be differentiated. And there is a requirement for you to remember the formulas that we use at GCSE. Now, as to specifically which ones you have to remember, because there's a couple on the formula sheet, I'm afraid I don't know. I'm hoping on February the 7th, when they do the pre-release information, that will be clarified. If not, I'll contact the examiner. You're then nearly always also given a rate. You're given a rate of some sort, and you're expected to combine those two things to make another rate. That's the sort of framework for these problems at their most basic. So let's have a look at this example here. So if you can't read it on the board, it's page 260 in the online version of the textbook, and if you have a paper version at home, it's page 261. In fact, I think it's page 261 in the online version as well. Okay, so in this question here, this is about the area of a circle, and they give us the formula. We would be expected to remember that normally. So that's the geometry fact. Now, in that expression, what is the variable here? What's the thing that can vary? Lily, what's the variable in pi r squared? The radius, yeah, r is the variable. Pi is a constant. Pi isn't going to change. So when I differentiate this, this is going to give me dA by dr. R is the variable. So it's a bit like differentiating 3x squared, except that's a pi and that's radius. So I'm going to multiply by the power and reduce the power by 1. And interestingly, when you differentiate the formula for the area of a circle, you get the formula for the circumference of a circle. There you go, isn't math one? What else are we told in the question? Well, we're told in the question the rate of change of radius, and they've given us how we write that, dr by dt, the rate of change of radius is 5. Now, that is in centimetres per second. What that means is that this circle is growing, and it's growing at a rate of, with its radius growing at 5 centimetres per second. So we might be talking about an oil slick or a circle in a pond after a stone's been dropped in. That's the rate at which the radius is growing. And what we're asked to find is dA by dt. That's the other rate we're asked to find in this. And that's the rate at which the area is growing. So this is the rate of growth of area. So we know that the radius is growing, but I hope you can understand that as the radius increases 5 centimetres each second, that's going to steadily increase the area rate, because to go from 5 to 10 centimetres, the area will increase by this much, but going from 10 to 15, that's a bigger increase. So this is going to be, this is not just 5 or something, it's going to be different. So here's what we do. We have got 2 d something by d something statements. One we were given, and one we worked out by differentiating the geometry fact. And we're being asked to find this third rate. So here's what we do. We look at what we've got here and we say, have we got an expression with dA on the top, like I've got there? Well, yes, look, this one here. Have I got an expression with dt on the bottom? Yeah, look, I've got this one here. What happens if I multiply those two together? And this is a little bit of a cheat, but we're just imagining those are fractions. We'd end up with dA dr over dr dt. We'd cancel out the drs. And we'd be left with dA over dt. Yeah, we're left with what we want. So I can build this by taking this and multiplying it by that. This is what the title is all about, related rates of change. I can build this rate of change, which is the rate of change at which the area is changing, using these two rates. This isn't a rate, but this is a rate because it's dt. That's just the relationship between area and the volume. Okay, so dA by dr is 2 pi r. dr by dt is 5, so I get 10 pi r. dA by dt, the rate at which the area is growing, well, if the radius is in centimetres per second, the rate at which the area is growing will be in centimetres squares per second. When r equals 3. So when r is 3, that becomes 10 times pi times 3, so that's 30 pi. And that's, at that instant, the rate at which the area is growing. The rate at which the area is growing will change. It's not going to be constant, because as the circle gets bigger, the increase every second in area will be bigger. Okay. Second example, same page for those at home. I'm just going to check this is still. So this starts in a similar way. We've got a geometry fact. In this case, it's the volume of a hemisphere. And we've also got a second geometry fact that the surface area is 3 pi r squared. I don't know why they bothered giving us that intermediate bit, I'm just going to write 3 pi r squared. So I've got 2 geometry facts, which means I can multiply them both. Sorry, differentiate them both. Slightly worrying, because this looks like it's going to be a more complicated example. I've also got a rate. dV by dt, the rate of increase in volume, is 6 centimetre cubes per seconds. Volume is 2/3 pi r cubed, if you can't read that, and surface area is 3 pi r squared. Remember, in both of those expressions, r is the variable. 2/3 of pi and 3 pi are constants. So I'm going to differentiate that, or you're going to differentiate that for me. I'm going to differentiate that. And I'm being asked to work out ds by dt. Joe, can I do a book or can I print something for you?
Yeah,
Mix exercise 30, 31 and 33 with the ones I've given. So this is just like, you know, something x cubed. I'm going to multiply by the power, reduce the power by 1. This is just like something x squared, multiply by the power, reduce the power by 1. Pi is just a constant in there. So I have my 3 d something by d something statements. I've got a rate, the rate of change of volume, dV by dt, and I've got dV by dr and ds by dr. So I'm going to look at what I'm being asked to make, ds by dt, and try and build it using those 3 rates. This is bound to be a little bit more complicated. Firstly, have I got something with a ds on the top? I have, right, yeah. Okay, so I'm going to write that. And then what I'm looking for is something with a dt on the bottom that has a dr on the top, so I could cancel out. So what I'm looking for, and sadly I can't find it at the moment, is dr by dt. If only I had dr by dt, I'd be happy. I've got this, that's all good. ds by dt, I've got that, that's 6 pi r. But I haven't got dr by dt. So there's a bit of work that needs to be done here. So let's see if I can build dr by dt. Now, I've used ds by dr, so it's unlikely to involve that. So what about the 2 remaining rates? I mean, we wouldn't have been asked to work them out if we weren't going to be expected to use them. And my heart sinks immediately because I can't see anything with a dr on the top. Could anyone suggest a solution to this? Go for it, George.
Flip the
You flip it. Yeah, the one that's got a dr in it is dv by dr. If I flip that, I get dr by dv. And we've already done that because we've worked out with some expressions dx by dy, and we just flipped it to get dy by dx. So that's going to be 1 over that. Just the reciprocal. We just flip it. I'm starting to feel a bit happier now, because if I want to make dr by dt, I've got the dr on the top, I just need something with dt on the bottom. Well, let's use that and then see what happens. Well, hey, the dv's cancel out, so it's all good. It's all good. Look, if I multiplied all that out, I'd have a dv top and bottom. dv by dt is 6. And go one step further. So that becomes 6 over 2 pi r squared, and 6 divided by 2 is 3, so I'm going to call that 3 over pi r squared. So I've built the thing I need here, and some of you might feel confident enough to do that in one sum. You might feel, be able to do that in one go. I'm not confident enough when I come to this, so I tend to find one of the ones which I can use and then decide what the other one will need to be. Anyway, I've worked out what that is now, so I can plug that back in. So that's, sorry, I know I'm doing a lot of this at the bottom of the board, so it's hard to see. But I get that, so I'm going to write that at the top of the board. So this is ds by dt, which is going to be 6 pi r times 3, 18 pi r over pi r squared. Take out my favourite pen, the cancelling pen. In this question, we're not given a value of r, so we found an expression rather than an actual value. But let's get the units right. This is the rate at which the surface area is changing. I could do a quick check. Yeah, we're talking centimetres and seconds, so that's going to be centimetres squared per second, or centimetres squared is to minus 1 if that's the way you would rather write it. So let's to the books. I'm going to give some books out. So this is a bit weird, but I'm not sure we're doing any particularly hard sums. Oh, sorry.
Yeah. Huh? No.
You're not getting it. So we are on page 261. No, we're not. I'm lying. Sorry. We are on page 263, questions 1 to 4. 263, 1 to 4. Which are a fairly gentle introduction to this. And then page 264, question 10, which is just a little bit more involved.
Could you please check your email?
Yeah, there's no update.
There's nothing going on around there.
Sorry?
Just make a run for it, I reckon, Joe.
I don't know. People, yeah, I think they've been. I think there's just teachers stood outside.
Oh God.
Yeah, Mr. Collins wasn't that people out earlier.
What, they could stand outside? What was the last time?
But it was the fire brigade that have asked.
I've not actually been to the entrance, I don't know. They
Oh.
were just,
The fire brigade have
What put I
just
have?
asked. I'm sure it'll be okay.
To do with some
Please say if you're completely lost. It's a bit weird, but I hope it's not too weird.
Sir,
Yes.
from question 2, if we
Yeah.
differentiate that, does it have to treat it as a...
Can't see it because I haven't got my glasses. Hang on. Sorry.
It's just x times b to the x, so just treat that as a product.
So yes, you're going to have to use the product rule for that. Yeah. Yeah. Number 2, you'll have to use the product rule. Well spotted if you spotted that. These, interestingly, don't have a context, do they? So there's no sort of centimetres or seconds, so there'll be no units.
Is that me?
You okay with number 1? Got it. Got to borrow.
Insert it in the flux brackets, so it's 2 and
Oh. Sorry, Grace. Sorry, Charlie. That was Isabel.
So,
Yes, Jacob.
is e to the x plus x times by e to the x similar?
So we've got x e to the x, so that's 1, and that's e to the x. So dy by dx is, you could write it as e to the x 1 plus x. Factorise it because they've both got.
But it doesn't really matter, does it?
No.
What did you get from this one? What, have you said didn't I equals 2? I've got pi r squared over 2 times by 6.
They left number 2. They left it in terms of e. So if you did it, what is 15 e squared?
So what was the answer?
Number 1 is 3 pi r. Does it give you, oh, was there a value? Did I not? Oh, and r is 2, so that's just 6 pi. 6 pi. So 15 times so 110.835 for that one if you. So sine of pi over 6 is a half, so you get minus 9 over 2. Oh, so with number 4, remember, this is just like 3x cubed, multiplied by the power. 3 times a third of pi is just pi, reduce the power by 1. Now I've got to build dr by dt, so no sign of anything with dr on the top, but remember what George said, we can flip the second one, sorry, flip this, give us dr by dv, which is 1 over that, and I need something with a t on the bottom, so let's try this, dv by dt, bingo, the dv's cancel out. It gives me 8 over pi r squared. When I substitute in r, that's just going to give me 8 over 9 pi. And no units there. Just because I need to move on, I've circled that one, page 264, question 10. We'll look at that at the beginning of the lesson tomorrow, so can you make sure you had a go at that one? Thank you. It's very similar, it's not complicated at all. It would be nice if that was the extent of what we needed to do. But there is an added level of complication, unfortunately. So let's look at some examples which illustrate that added complication. So in that last question, we ended up with an expression for, sorry, in that when I say that last question, I know some of you are on to 10. In number 4, we ended up with dr by dt equals 8 over pi r squared. This is the rate of change in that question of some value r. It didn't have a context, so we don't know actually what r is. But there's another word for this. This is also referred to as a differential equation. It's an equation, equal sign, it's an equation, with something that's been differentiated in it, in this case dr by dt, a differential equation. We meet differential equations later in this term when we talk about integrating, but that's a phrase you need to be familiar with. These d something by d something statements are known as differential equations. So have a look at this example 29. We're back to page, where I scheduled to page 262 now for those of you. So the decay of radioactive particles, the rate at which particles decay, so that's a rate at which the number of particles decay. So I need to call that something. I firstly need to find my whiteboard rubber. Where have I put my whiteboard? Let's say the number of particles are left is n. So the rate at which the number of particles is decaying is dn by dt. So I've just made up that letter. I could have used whatever letter I want, x, y, whatever. I've used n for the number of particles. Now we're not given any formula. There's no, area of this, volume of that. We're not given any rates, but we're asked to write down a differential equation for the rate of change of the number of particles. That's what that is. So we've got to write something about that. What is that equal to? Well, all we are told is that it is proportional to the number of particles remaining. Now you may remember from GCSE we used this symbol to mean proportional to. That means as one thing increases, the other thing increases. And if one thing is proportional to another, there's a multiplier that links them after divided by before. And so what we can say is that the rate of change of the number of particles is equal to some multiplier, that's a constant, some constant times n. Now there's only one subtle thing we need to add. This is definitely a negative rate. Something is getting smaller here. And so we could say, so that means k is going to be negative. But what we tend to do is we tend to put a minus sign there to indicate that this is something getting smaller, and therefore k is going to be positive. So that's all that question means. dn by dt is equal to some multiplier times n. That's what this sentence the rate at which particles decay is proportional to the number of particles remaining. That's what that sentence means. So let's look at a final example which combines these two things, the building the different statements and this proportional type statement, okay? The head of a snowman of radius r loses volume by evaporation at a rate proportional to its surface area. So the loss of volume, so that's the rate at which the volume is changing. So we know that dV by dt, that's the rate at which the volume is changing, dV by dt is proportional to the surface area. I'm going to use A for surface area. So what that means is that dV by dt is equal to that. And this is something which is getting smaller. Perhaps I'll clarify that where we're then given some formula, like in the first sort of examples, we're told the volume of a sphere is equal to 4/3 pi r cubed, where r is the radius, and the surface area I've called A, so I've called that A, is equal to 4 pi r squared, 4 pi r squared. Those are two statements I can differentiate, dV by dr and dA by dr, which will give me dV by dt, dV by dr, dA by dr. I'm asked to write down a differential equation for the rate of change of radius. So what they want is dr by dt. dr by dt. So go on, see if you can differentiate that, see if you can differentiate that, see if you can have a go at building that from the three things we've got. It's still no word. Why don't you pop down to common room? See what it says. Did sort of Matt Evans better than Escape? I'm sure it might be. I don't think you are. What do you short for? Have you got money on you? So you're trying to differentiate the two expressions, V equals A equals. Remember, R is the variable, so 4/3 of pi and 4 pi are both constants. I'm going to multiply them by 3 and by 2 respectively. And there's a number of ways you can build that final statement, so you may find you do it differently to me. Now, if you've got to the end of this, you'll realise that we've done more work than we needed to. But at the beginning of the question, we didn't really know what it was we needed to do, so that's not a huge problem. Now I need something with dr on the top, and I've got two things that I could flip. So I could flip dA by dr, I could flip dV by dr. So let's do it the way that won't work. All right? If I flip dA by dr, I'd need something that had a dt on the bottom and a dA on the top, dA by dt. Now I haven't got a dA by dt, and I couldn't build it from these things because they haven't got a dA in them. So if you had a go with it by flipping that, that would have failed. Let's try flipping this one instead. Now if that's going to work, what do I need to put here? Well, I need a dt on the bottom, and ideally a dv up there to cancel that out. So the dv's would cancel out, I'd be left with dr by dt. Ah, I've actually got that. So I've got dr by dv, I just flipped that one. 1 over 4 pi r squared, sorry I'm down the bottom again, aren't I? I've got dv by dt, which is minus ka. Now we haven't quite finished with that yet, but clearly I didn't actually need to do that. Didn't need to do that. I'm not going to use dA by dr. However, I didn't know that to start with, and it's, you know, it wasn't like it took me 10 minutes to do that. But yeah, we're not going to use that. Right, let's see if we can simplify this, because at the moment it looks a bit grim. So I'm going to go to the top. So we've got minus Ka, so this is dr by dt, minus Ka over 4 pi r squared. Now that doesn't look very pretty, does it? But I've got a formula for A. A is 4 pi r squared. So I'll tell you what, let's rewrite it. But let's replace A with 4 pi r squared, the formula for the area that we're given in the question. All of a sudden, not too bad, does it? I can take out my favourite pen. 4's cancel, pi's cancel, r squared's cancel. So the answer is just minus k. Simple as that. We've met 2 of these proportional questions. Can I just remind you from, I say remind you, it's a long time since GCSE, I know. Your end of year 11 was a little bit disrupted. What's the one I want to show you? Question 9. Oh, sorry, just to say that we didn't have a value to substitute in with this last one because they said they wanted a differential equation, and that's what we've got. That is a differential equation. So with this one, this is again is an easy one because there's no, you know, malarkey involved. It's just writing down what that means. So the ice on a pond has a thickness x, and the rate of increase of x dx by dt, and it's increasing, so it's going to be positive, is inversely proportional to the square of x. So you may remember that we used to write inversely proportional to the square of x like that. So what that means is that dx by dt is equal to some constant times that, which we normally write, sorry, not k squared, we normally write like that. And there are all sorts of proportionality, you know, so it could be proportional to x squared, in which case it would be kx squared, proportional to the square root of x, in which case it would be k root x, could be inversely proportional, it would be k over x, or in this case, inversely proportional to the square of x. So that is that. Okay, so actually we've got 5 minutes left, so let's pick up question 10 if you didn't finish it, and see if we can go to question 11, and then tomorrow we're going to spend a little bit more time on this because it's worth working through some examples.